I guess that means we should start. Okay, so the plan for today is to finish off this stuff on manipulating language objects in R, and then to launch into talking about Python. And that will probably last into Friday, and we may get a chance on Friday to start on yet the next unit, which is on parallel processing, which I'm slightly behind on getting up, so is not up yet on GitHub. Okay, questions from last time? Okay, so I thought what I'd do is, we've talked about this idea that R takes any code that you're passing into it to evaluate and basically manipulates that text and parses it and creates this tree structure that it can then evaluate. And basically, if it's got a sort of nested set of function calls so it can work its way through that tree, evaluate what it needs to, plug it in, then continue evaluating until it's able to evaluate the full expression. So I had some examples in, I guess this is 6.2 of the notes, but I thought what I would do is change things around slightly and just do a sort of slightly more complicated nested example just to see that and illustrate the same things that I had in the demo code. So what we're going to do is look at this expression, which we already saw that an expression like this. So the idea is that there are three different, well, I guess 4 different function calls embedded in here. And the top level call is going to evaluate the result of doing another call, the plus, and that is the result of then evaluating 2 calls itself in the argument of the plus. So we're going to create this object E, and now I'm just going to say, well, let's look at E as a list, which is the way that we can sort of print out these language objects in a way that allows us to get a better understanding of how R has structured this tree. And in general, as I said, I think last time, basically the way these things are structured is basically the first element is going to be whatever the function call or whatever the operator is. And then the next ones, in this case there's only one, are going to be the various arguments that get passed into that function call. So in this case, the mean function is really only taking one argument. That argument happens to be a fairly complicated expression, but once this gets evaluated, that's just going to be a single input that's just going to be a vector. So that's why this thing is just a single element here. But then the idea is that we can sort of burrow down into what R is doing in terms of constructing this tree by actually looking at pieces of this. So we could say as.list of E of 2, and that would say, well, the way that R is thinking about that piece of the code is, well, that's the plus function or the plus operator applied to 2 different, not applied in the official sense of the apply function, but the plus function used with 2 different arguments. And we could continue this, this level of burrowing in as much as we want. I could then say, okay, well, the third element of that is the R norm of 3. So if I now just keep subsetting into the list, then I can get down to, well, that's just a call to the R norm function. In this case, that just takes one argument, 3. And then, of course, when R norm actually gets evaluated, it's going to take in 3. It's going to realize that it doesn't have it's going to realize that we didn't pass in the mean and the SD, so then it's going to have to go and get the default arguments and so on. But in this case, in terms of actually evaluating the code, only one thing is getting passed in. Okay, so let me pause there and see if there are questions about that tree structure or how we're getting access to those pieces. Okay. So all of that stuff, all the stuff for doing the evaluation is now in this language object, this E object, and if we want to see the pieces, we've just seen how we can do that. I can also evaluate language objects by just, if I've converted to a list, I can basically convert it back to a language object that can then be evaluated by doing as.call, as long as the language object is one of these various call operations, a for statement, an if statement, an operator, a function, etc. So in this case, I could say, let's go back. I guess we already looked at this. This was the R norm of 3. Oops. So that's this. Before I convert it into a list, that's this language object, and now I convert it into a list, and now I can convert it back and evaluate it by saying as.call on that. So that converts it back into something that sort of looks like one of these language objects. You notice it's not in quotes, so it's not actually a character string. It's actually in the form of one of these language objects. And if I actually want to evaluate that, I can call the eval function, and that will just give me back the result of our norm of 3. So I have quite a bit of power to sort of cast things or coerce things to be one kind and then back to another and then off to another and things like that. And I can also, as we'll see in a second, convert things from just simple strings to any of these sorts of things. Yeah, Dustin?
Why couldn't you just evaluate E2, 3?
Because, well, that's a good question. Let's see if we can. I was going to say I can't if I'm looking at this because I've converted it to a list, but we might be able to just do the E2, 3. So let's see. I guess I'll just leave all the parentheses in there. They're not going to do any harm. Okay, so that works as well. Yep. So yeah, so that was in the form. I guess that suggests, I hadn't remembered this, but I guess that suggests we can sort of nest into this as if it's a list, but it's still interpreted by R as one of these language objects. So we can indeed just do the eval of that. Daniel, feel free to jump in. I know you've been looking at these things a lot recently. Okay, other questions? So, okay, so that was this use of eval. We can actually manipulate the tree as well, and these examples are going to be a little bit silly. I probably should have worked a little harder to come up with a more realistic example, but this will at least illustrate it, and they're kind of fun because you can do sort of silly stuff with it. So I'm going to create a simple language object where I'm just going to assign y to be 3. But now I'm going to go in and manipulate the actual language object and change around the pieces of the object. So I'm going to take, so if I say as.list of out just to see what it looks like, well, as we would expect, the third element of this is the 3 that's getting assigned into y. So I could actually go in and change that. Now if I do as.list of out, it's going to have 4 in that place. And then now I should be able to evaluate this. And y should indeed be 4. Okay, so I've gone in and manipulated the language and then evaluated it. So that's sort of a very powerful thing to be able to do, that I've actually modified the code in this fashion. I can do even sort of sillier stuff like, what's that? Oh, okay. So suppose I make E1 an expression that's just 4 plus 5, and I make E2 plot of x and y. Okay, so now I could change, so E2 in the first position is going to have plot. This is going to be the first element, and then the second element, and then the third element. So why don't I just change this to a plus? I can just change the function call entirely. As I said, this is a little bit silly. It's not clear exactly when you might want to do this. But if I do that, and now I say as.list of E2, you can see that we've got the plus in there. It looks like it's interesting. It doesn't just have it written out as a plus with backticks, which is how it would have, how it presumably looks with E1. But I think it will do the same thing. So let's evaluate E2. Actually, I guess we don't know what's in x and what's in y. Okay, good. So x and y are 3 and 4. So it did actually, it was able to evaluate this E2, even though the parsing gave us this somewhat more involved expression for what the plus is than just simply the plus backtick. Although actually, I mean, if we just look at the plus, we can see it just gives us that language. So that's actually the same thing as was there. Okay, so as I said before, we can also convert back and forth between strings and language objects, and we can evaluate things in various different directions. So so out was that, it's just a language object. I can convert it back to a string by using the dparse function. So parsing is basically taking language and then creating this tree out of things, and so the idea is deparsing sort of goes back from the language back, and in this case it converts it back into text and into strings. So if I look at this, we see, okay, that's actually now a character string. You can see it's in quotes, so it's not actually being represented anymore as a language object. I can also take, so we've already seen the use of quote that will take our statements and create this tree structure and parse the language and create this tree structure. We can also do the same thing but with text coming in. So here the code text is just this y gets 4, and if I say parse and pass that in as the text argument to parse, what we'll see is that the parsed code now looks like a language object. In this case, it looks like it created an expression out of it, which is basically an expression is basically going to be a vector that has multiple of these language objects in it. In this case, it's just going to be a one-element expression. But I should be able to do something like the same sort of as.list business with this as we were seeing before. In this case, it's showing up as the first element is the whole thing, so I need to nest into that, and then we can see that once we get inside that first element, it looks like the same sort of language objects expressed as lists that we've already seen. And I can indeed evaluate that code as well, and that should do the assignment of y to 4, of 4 to y, I mean. And if I wanted to go from something where I used quote to create the language object to then deparse it and get back the string representation of that, I can do that as well. So I have sort of complete power to go in any sort of direction that I might need to go. So one place that comes up is I lost track of where I am. Hold on a second. Oh, okay. I'm showing that later on. Okay. So then the last thing I wanted to mention, and this again uses this idea of casting from one type to another and of using eval, is I can manipulate names of objects as well. And this is something that is maybe a bit more practical and you might be more likely to run into sooner rather than later, as opposed to some of the stuff I just showed. So suppose that I have an object x3 and I create an index value that I'm going to call I. I can create the name x3 by pasting together x and I, and then I can say as.name, and that's going to allow R to interpret that as the name of an object. So you notice again this is not in quotes, so R is treating this as a language object. And then I could say eval of this, and I'm going to get back the 7 that's stored in x3. So for example, if somehow or another you had a whole bunch of variables x1, x2, x3, x4, x10,000, I think maybe I already said this in a previous lecture. Anyway, you can programmatically refer to, you could programmatically, for example, loop through I and pull out the x values that you're interested in rather than having to type in the particular x, having to type in x1 or x99 or x73 or whatever. And you can do the same thing. You can do similar sorts of things by using the assign function, which will, I think we've already seen that a little bit, will basically assign into, if this is a character string, it'll assign into an object with that name whatever value you give. So again, you could create this string on the fly by pasting together the different pieces of the name, perhaps essentially with like an index value in there, and then you could assign into it. So there's a lot of power here in manipulating names of objects as well. Okay, questions? I'm going to skip 6.4, which has to do with parsing replacement expressions, because it's maybe a bit esoteric, and I'd rather move on to the Python stuff. So let me skip that and then just show you a little bit of the use of the substitute function. So substitute in some ways acts like quote. So it's basically allowing you to take, it's allowing you to type in or create basically text and then have R interpret that as language and not actually go and evaluate the code right away. So if I say, are those two things identical? It says, yep, those are the same things. But the nice thing about substitute is it allows you to manipulate the expression and basically substitute in for pieces of the expression. So the idea here is I'm going to create an environment E. So this was sort of something I skipped over last time, but I can create a new environment with new.n, and then I can assign objects into that environment with the $sign notation. So I'm going to do that, and the reason I want to do that is then what I'm going to do is I'm going to use substitute and pass in an environment, and what R is going to do is it's going to look in this expression. It's not going to evaluate it. It's going to look in it, see if any of the symbols in here are in this environment, in this case E, and if there are, then it's going to substitute in. So you'll notice I defined EX to be 3, so it's going to say, oh, there's an X in here, there's an X in here. I'm going to substitute whatever the X is in for this environment into the language expression. So this is another way of sort of constructing statements in a particular context. So if I do that, you can see now I have Z gets 3 squared instead of Z gets X squared, and I could, for example, go ahead and evaluate that if I wanted to. This also allows you to do sort of weird stuff, just like when I was manipulating the parse tree of the language object and I changed the plot to a plus or things like that. I could have done sort of crazy things there, like I could have changed plus 3 and 4 to be 5, 3, and 4, but then the 5 is no longer a function call, and that wouldn't make a lot of sense. I can do sort of similar things here. Suppose I assign Z to be 5 in the environment E and now substitute in, this should now substitute in for both X and Z, and it does that. And so if we actually tried to evaluate that, presumably we're going to get some sort of error here because we cannot assign values to numbers. Okay, yeah, so it says it's invalid to do this left-hand side assignment. Okay, so the other thing I wanted to show you was a practical case where R uses substitute. So let me go back to the PDF. And if we look here, when we do a plot in R, for example, if I do this in R, you'll notice what it did was it took whatever was passed in as the arguments for X and Y, and it actually made them into the labels. So it's doing something behind the scenes to be able to grab that information and basically convert it into text that it then pastes onto the axis labels in the plot. So if we actually went and looked to see what was going on, what we would see is some syntax that looks like this. X label, well, there's something about missing this, but let's assume it's not missing. And here's the guts of it. It uses dparse. That sort of makes sense because we saw that dparse is something that converts from language to text, and the text is what needs to get passed in as the X label or the Y label. And it actually used substitute here. So if we make a function call like this, remember promises from when we were talking about functions, R is not immediately going to evaluate X equals R norm of 5. It's not going to immediately have X be a vector of numbers. It's going to carry around the R norm of 5 and have that associated with X as one of these promises. And so at this point, when this happens, X is still sort of bound up with this R norm of 5, and so the substitute will basically substitute in for X whatever the code was that is associated with X at the moment. And then that's still a language object after we've done the substitute. Then the dparse then converts it into a string, and that string can then get passed in as the xlab argument in the plot function. So that's an example of some of this language manipulation going on in some of sort of the core functionality in R. Okay, questions about that? Comments? Okay, so I had a sort of little toy example here that basically illustrates that without getting caught up in all of the stuff that goes on in plotting, but I don't think we need to go through that. Here's another example of doing this substitution. I don't have to have a list as the thing that I'm substituting from. I don't have to have an environment as the thing I'm substituting from, and instead I could have a list, just a named list, and so it should substitute in for this. It should substitute a 1 for the A, and it should substitute an X for the B. So why do I have quote of X here? What do you think? What might happen if I don't have the quote of x? Yeah, what it will do is go grab the value of whatever x is and put that in. So I would have 1 plus, and let's say x was 5, I would have 1 plus 5 instead of 1 plus x. Okay, so again, this idea of we need to tell R that we're sort of abstracting away from actually evaluating code to manipulating the language itself, and that's why we need the quote. And then I just want to point out here that I could do things if I wanted to. If I actually had a language object already and I want to substitute it to that, this would not work because substitute doesn't actually evaluate E1. It would just try and look for E1 within this list or within any environment that I pass here. So if I actually want to substitute into the things that are in E1, you have to do multiple substitutes, and sort of you have to sort of get your brain around sort of substituting it multiple times. So I don't think we need to go into that, but I just want to point that out because that occasionally comes up, and so you may need to go sort of delve more into that. Okay, so I think that's all I want to say about this manipulation of language. Are there any questions before I move on to the next unit?
So the substitute function, if you don't pass it any environment or list, where is it object?
Didn't quite follow. If you don't pass any list or environment, it'll basically just act like quote. It'll just return you back the language object. Yeah. And if you pass it something where if you give it a context in which it can look for stuff to then do the substitution, then it will go ahead and do that. Yeah. Although I guess we already saw with the promise in the function call, it will actually grab the language, the code that's associated with the promise in the case of the function. And presumably quote would not do that because otherwise they might have used quote in that plot situation. Okay, so let's go on to Unit 7, which is the Python unit. This is sort of actually it's a momentous time in the course. It's sort of a break between when we're really focusing on learning R and when we're going to be focusing on lots of other topics, and we're going to use R as a tool to explore those ideas. So basically from this point forward, the next unit, as an exception where we're really just looking at Python, we're going to be talking about very more general concepts and other things, but we're still going to be using R to explore those ideas. And there's no reason that we couldn't, for example, do the rest of the course in MATLAB or in Python or in some other language. It just, since a lot of statisticians use R and a lot of people in the department use R, the idea was that the course would be structured around using R. Okay. Where am I? Yeah. Okay. So this is actually a new unit. I haven't done this the last couple of years, so it's a bit of an experiment. We'll see how it goes. Keep that in mind as we're going through it, because when you have the final course evaluations, I'll be interested to hear what you thought of covering Python briefly in the way that I'm going to do here. So the basic idea of showing you some Python is basically to basically illustrate some of the programming concepts that we've already seen in R and show you that they come up in other languages, to illustrate the idea that now that we know one language really well and know some of these programming concepts in one language, we can use those to be able to pick up and learn other languages fairly quickly. And then the final goal is that for those of you who are in the Stat Masters program, the Masters Capstone course, 222, next semester is going to rely heavily on Python, so this will give you a little bit of a running start to get you prepared for that. So those are the goals. So what I'm going to do here, and the danger in this unit, I think, is that I'm going to try and show you a little bit of the details of how to use Python, but we're not going to spend a lot of time on it. So the danger is that we sort of don't spend enough time on it for you to really learn it. So anyway, so we'll see how it goes. And like I said, I'll be interested in your feedback. I'm hoping the idea was part of the hope is that because we've seen R, that we can see some of these concepts, and it won't be that hard to pick up the syntax and at least be able to understand what's going on, because the syntax is in some ways not all that dissimilar from R. The other thing I'll mention is, so I did that little poll of you guys last class where I asked how many of you had used Python. It's entirely possible, in fact, reasonably likely that there are at least a few of you in the audience who know Python better than I do, because I don't know Python all that well. So I'd be happy for you guys to speak up, and I encourage you to speak up. And if you think I'm saying something wrong, or it's not quite how you would see it, or if you had something to add about Python that you think would be useful for the others in the class to know, please do jump in. Okay, and then the final note is that knitr is not really set up to work with Python. So basically, I just have the code pasted in here. I haven't actually evaluated the code within this document, and so I'm going to go over to a Python session and be evaluating the code in that Python section, as opposed to using, for example, RStudio. Okay, so the idea is Python is another one of these interpreter languages, like R, like MATLAB, like a variety of other languages. So we don't need to define what types our various objects are in advance. It's fairly heavily focused on object-oriented programming and built around that. And it's very good at a number of things, in particular string manipulations, at interacting with the operating system and interacting with other programs. So lots of people use Python as basically sort of their master controller language, and from within a Python script, you might then call some R code, or you might do some bash Unix stuff, or you might go interact with the database, and you might combine all of these operations in a single workflow, all of it managed from within Python. And so Python is quite good at doing that. So the other thing about Python is, like R, there are a variety of ways we can interact with it. We can start up just a simple command line Python session, just like we start R at the command line, we can start Python at the command line. There's a nicer, more interactive version of that command line called IPython, which we'll see in a second. And then there's a graphical interface that's been developed over the last few years, and that development is heavily concentrated here at Berkeley, and that's called the IPython notebook. So this has some similarity to what we've seen with RStudio, and allows you to do some pretty nice stuff. So let's actually switch over here. Where do I have this? Okay, so I just have an Emacs window open with the Python code from the class, from the unit. And let me quit out of Python here. So I'm going to start, for the moment I'm going to start up IPython. I'm going to have to switch back and forth because indentation matters a lot in Python. It's actually how you determine where functions start and end and things like that. And the problem is when you start pasting from different places into your Python session, sometimes the indentation gets messed up and it'll give you back an error. So I may need to sort of adjust on the fly here. But this is IPython. And you can see, it starts up in a somewhat different way than R, but it basically gives you a command line at this point, and you're sort of in the same boat you are if you start R and don't know anything, like, what do I do now? I don't know what to type, right? So here's just some basic syntax. You can do the same sorts of things in Python as you do in R in terms of doing arithmetic and math and stuff like that. So I'm going to print out a little bit of stuff, and I'm also going to illustrate that this 5 was an integer, this 2.1 is a floating point. It was able to, behind the scenes, do the coercion of one type to another and print out something that's a floating point. So the same sort of thing as we see in R, that it'll handle things behind the scenes. I can't do this. So in R, it wouldn't matter if I put some spaces or tabs in front. But if I do this, Python complains that there's an unexpected indentation. So if you're just running code, you can't have any spaces or indentations. You need to start right at the beginning of the line. And then the indentation is basically indicates blocks of code within, say, an if statement or a for loop or a function definition or that sort of thing. So you'll see in Python that it's pretty clean, and there's not a lot of sort of squiggly braces and stuff like that indicate code blocks. And the reason is Python does that by indentation. So I think that's a pretty nice feature. A lot of people like that, and it makes it pretty easy to read the code. But as we've seen, it might make pasting and cutting and pasting a little bit of a hassle. So we can do comparison kind of operations. There are booleans, logicals in Python as well. We can ask what kind of object different things are. So here we should be able to see that some things are integers, some things are floating point decimal numbers. So we're seeing that here I can ask whether the dist object, which we defined further up here as being 7, we can ask whether it's an integer. It says it's true. So A lot of this is stuff what we did in R, but the syntax was a little bit different. But basically the way I think about Python and MATLAB and R is for the most part, anything that you can dream of doing in one of them, there's a way to do it in the other one. You just have to go and figure out what the syntax is that sort of translates from one to the other. And there are some different motifs of how you execute calculations in some of the different languages. But in a lot of cases, you can basically sort of know that there should be some functionality. And then once you know that exists, then a little bit of Googling around or looking at a manual will often get you to the syntax that you need. Okay, so I've sort of now given you a bunch of introduction here. Any questions so far? Okay, so here's a little bit of string manipulation. I'm going to create some character strings. You'll notice I put a new line in here using the /n. And in Python, I can concatenate character strings with a plus. So basically, Python has done something called overloading, where usually plus, if we take plus and give it two numbers, we'll add together the numbers. But Python has overloaded the plus operator such that it can operate with strings. And the obvious thing to do when you add together strings is to concatenate them. So that's exactly what this is going to do. The other thing that we'll notice here is there's a bit of object-oriented programming going on, which is that name is a string object in Python. And string objects have a bunch of methods with them, just like we saw with object-oriented programming in R. And if we have an object and we say dot and then the name of a method that can get used on an object of that class, it will then execute that. And in this case, this is going to capitalize this. We don't need any additional arguments because all the capitalize needs to know is what object am I operating on, and that's already embedded in the fact that we're using that, we're applying a method to that object. So there's no nothing else there. So you can do that. That seems pretty slick. Looks like it didn't actually explicitly print out the /n. I don't know off the top of my head, but presumably there's a printing style function that would actually print that out in a way that actually invokes the new line. Here's another object-oriented string operation. I can split that intro string based on a space. So this is just like the string split in R, except maybe a bit more elegant in terms of the syntax. And this gives us back sort of what we would expect, a bunch of different separate strings. We're going to see this in a second, but this is a list in Python, pretty similar to a list in R, in that you can basically have heterogeneous objects captured within a list. In this case, it's a list that happens to have all objects that are strings, and we could index into and pull out each of those elements of this list. Another nice aspect of this is we can actually index into elements of a single string. So remember in R we had to do substring, and then we had to give it the name of the string, and then we had to say position 3 to position 5. So it was a little bit what's the word I'm looking for? You guys probably know what I mean. And you might have, as you were doing that a bunch in problem set 2, you might have said, oh, I wish I could just do indexing into the string itself, with square brackets. Well, in Python you can actually do that. Here's a string and I can just index in, and this says go from the 0th position to the 10th position in increments of 2. So that's what this colon operation does. Python is zero-based indexing, so the first element in a Python object is the 0th element and on to the n-1th element, so you have to remember that. And that's the sort of thing that would cause bugs as you convert from code from one language to another, is if you forget to change the indexing. So if we do that, it does indeed take out the 1st, 3rd, 5th, 7th, etc. elements of that string. Okay, so here's an if statement in Python. In general, blocks of code like function definitions or if statements or for statements are going to have a colon at the end like this. And then basically you indent the pieces within each block, and then if you start a new sort of subblock within the if statement, like an else if or a final else, then you need to bring it back to the previous level of indentation. So that's basically how you would structure it. You notice there are no squiggly brackets ending and stopping things. It just is done based on the indentation. So I think this is not going to work when I paste it into IPython, because I think I was trying this morning. Yeah, it didn't like my pasting. I haven't actually gone and figured out how to use the %paste So instead, I think this worked when I started Python itself. So I'm just going to, out of laziness, do this instead in, oh, I guess I need to paste the whole thing in here because I've got name defined earlier. Okay, so here this Python and IPython are fairly similar. There's a little bit less functionality, as we'll see in IPython, but for the sake of this illustration, it doesn't matter. So it just went through and did what we would expect. It evaluated this condition, said is it true or false. If it's not true, it goes down here. Evaluates this. If it's not true, and continues on. It could have many else if statements. And in this case, this turned out to be true, so it then printed this out. Again, I'm doing some string manipulation here in the body of what gets evaluated there. And I can do for loops. Again, this doesn't quite look like a for loop as in R, but it's not too dissimilar. And the syntax, again, in terms of indentation of the colons, is sort of like what we saw in the for loop. Range of 10 is basically a way of doing, like in R, we would do 1:10 to create 1 up through 10. This is going to create a set of indices 0, 1, 2, 3 up to 9 automatically for us. And we're going to loop over that. In this case, the plus equals says take x and sequentially add I to it. So this is basically x equals x plus I. Those of you who know some C or other languages will be familiar with that syntax. And then you'll notice the ... it was sort of expecting me to continue because I had done an indentation. I could have done another indentation and put another line, and I just hit return, and then it knows that I'm done with the block of code, and it should actually go and evaluate it. So if I type x here, it should print out the result of adding together whatever range of 10 is, which should be 0 up through 9. Okay. And you'll notice this is in the form of a list. We can tell that because it's indicated in these square brackets. Okay, any questions at this point?
I just noticed that in this for loop you indent more than in the
Yeah, I didn't mean to do that. I think I was having some trouble with my editor in terms of having the indentation come out quite right, which might be why I'm having some trouble with the pasting. So really, yeah, this and it's a little bit unfortunate because it does actually matter in Python. This should just be a single indent here, a single tab. And if you have blocks that are sort of nested within blocks, like you had a function definition within another function definition, you would then have multiple tabs or indentations to sort of push things in even further.
Excuse me, what if I want to loop from 1 to 10, so how should I do that?
If you actually wanted to literally loop from 1 to 10 and not 0 to 9, well, you could, for example, just add 1 on, I think. Oh, that's not going to work, right? Which we'll get to in a second. Yeah, I'm not sure. Does anybody know how I directly do 1 through 10 here?
I think you can put min and max arguments.
Okay, that sounds reasonable. Min equals 1, max equals, we're just going to try this on the fly. Okay, so actually this is a good, I'm glad Zoe raised that question because we can actually now go on to figure out how to get help on things in Python. So if we do help of range, it should give us some information about how to call the function. So it looks like we can just give it range 1, 10, and that should do it. So it gives some information about the arguments and then gives some information about how you'd actually carry things out. So Python is pretty good about providing help information. I think it's actually not quite as nice as R because R tends to have a very voluminous set of help information, including examples and a bunch of details often, and so sometimes it seems to me that the Python help is a little bit less extensive, but it is there is quite a bit of help information. So it looks like we can do this. Okay, so that worked. Although actually it only went up to 9 again because having to do with this 0-based indexing. So it looks like we need to actually trick it that way. Yeah. Let's see, what else was I going to... Oh, right. So if we're in IPython, but not in Python, so I need to make sure I'm in the right place here. This is IPython. There's some really nice functionality for figuring out what kinds of methods are available for objects of a particular class. So str is a string. It's actually perhaps confusingly named because if I type... getting doubly involved here. If I type the word type on the object string, we find out that it is an str, which is a string. Anyway, the point of that was not to get me tongue-tied, but if we do str dot, and then we then want to know what kinds of methods can we apply to an object of this type. If I do tab now, it's going to print out all the different things that I could do with this object. So that you could imagine this is incredibly powerful. I have an object. I know I want to do some manipulation with it. All I need to do to find out what methods are associated with objects that are like that is to do this. And this is basically the universe of a large part of the universe of what you might want to do with strings. And it's all, oftentimes it's going to be obvious even just from the name what it is that it does, at least in general terms. Yeah.
Are there hidden ones in the list?
Are there hidden ones? What do you mean by hidden?
Like in R, we only construct a class. You might have some methods, which is actually.
Oh, right. I don't know if there are hidden ones or not. I wouldn't be surprised if there were. Is anybody who knows more Python than me able to answer that question? No. Okay, yeah, I'm not sure, but there may well be some similar sorts of things where there are sort of methods that are only available sort of within the body of other methods that are defined for some particular package of functionality. I can presumably do help of things like this. Yeah, so this will tell me how to work with the strip method for the string class. Okay, other questions? Actually, I'm sort of curious if I do str and then just do tab. Okay, so I need to put the dot in to let it know I'm looking for methods. Okay, so Python also has an extensive set of packages, just like R does. Again, the idea of that we can have a sort of very functional language, but there's always going to be new stuff that people are dreaming up that one wants to add into the language, but that we don't want that necessarily all bundled up with the core language, because if I'm working in some domain, if I'm working on astronomy, I don't want all of the packages that are useful for economics loaded into my workspace, sort of getting in the way and using up memory and things like that. So just like in R where we do library or require and then give a package name, in Python we use import and we give the name of the package that we want to import. You'll notice this doesn't really look like a function call, it's sort of more like a command because it doesn't have parentheses. And I can then use the functions and objects defined in that package. So I do that again with object-oriented notation of using a dot. So I'll say, okay, the name of the package that I've imported, and then in this case, this I guess this isn't really a function, more of an object. And then either the function or object I want to use from within that package. So if I do that here, what I'll get back is this gives me the value that's of the home environment variable from the Unix shell. So the OS is for interacting with the operating system. I can also do some nice things. I can import a package. So NumPy is basically the core package used for doing numerical calculations. So I could, instead of, here I had to type OS, and if I imported NumPy without this, I would have to type the 5 characters NumPy every time. And some of the packages have much longer names. So I can give it my own name by saying as. So then I can operate as np and then names of things within the package. So if I do that, it's going to take a second or so to do that loading. And here's how there are multiple ways to generate random numbers and random normals in R, but one way to do it is through the NumPy package that I'm going to call, I guess this is a sub-package, I'm not quite sure of exactly the terminology here, but there's some set of random number functionality, and then within that I can call normal, which gives me random normals. And in this case, the argument that I give it is size to get 1,000 standard normals. So then if I look at VAC, a lot of things in Python are going to be provided to us as lists, so I would be surprised if this were not a list. Although actually, let's look at this. What did I call it? VAC? Oh, right, okay. So this is actually a NumPy array, which we'll talk about in a little bit. So NumPy arrays are sort of the core building block of actually doing mathematical operations. So you'll notice before I tried to add 1 to a list, and it wouldn't do that because lists are not really set up to do vectorized numerical calculations. So the NumPy arrays are the things that are set up to do those sorts of things, as we'll see in a little bit. But I can then do operations on that NumPy array, which are numerical kinds of operations. And again, like we were doing with the string operations, this is now a method for these NumPy arrays, the mean method, and that will do the sort of obvious calculation. And of course, we could do the same thing here of doing tab completion after typing the dot and see all of the various things that you can do with a NumPy array. And there are lots and lots of them. Just a side note, if you're interested in regular expressions in Python, it's the RE package, so that might come in handy. Okay, so that was a little bit of sort of basic introduction to Python. Yeah.
So is this Python 2 or Python 3?
I believe this is Python 2.7, I think. So Python is versioning Python 2.x and Python 3 have a number of dissimilarities, and my understanding is how does the that you can run Python 2 code in Python 3. You can run, I think for the most part you can run Python 2 code in Python 3, but you can't. It's not sort of backwards compatible. If anybody who knows more about this wants to chime in, feel free. No, okay. Yeah, it's not sort of clear to me. A couple years ago, when I took the Python bootcamp with Josh Bloom, who's an astronomy professor, at that point Python 3 existed, but we were still using Python 2 in the bootcamp, and it's not totally clear to me whether people have really migrated wholesale over to Python 3 or still people are mostly using Python 2. It presumably actually said at the top, oops, let's just quit out of this and see if it says at the top. Actually, I think it's exit. Yeah, so this is a particular packaged up distribution of Python provided by a company called Nthought, and it's version 2.7.3 of Python. Okay, so the idea of this next part of the Python unit is basically to do a compare and contrast of how things work in Python compared to R, and see some of these concepts that we've already seen in R revisited from this different angle. So let's talk about different kinds of objects in Python and see in what ways things are similar to and dissimilar from R. So I can create an object in Python. I can reassign, the name of an object to first be a number and then be a character string, and Python has no problems with this. So it's dynamically typed. I don't have to say in advance that the object data is going to be a number forevermore. I can just change things on the fly. I can create a list with square brackets, and you'll notice that just like lists in R, I can create nested lists, and I can create lists that have heterogeneous kinds of objects. So here I've got a number, I think this is just going to be an integer by default, a Boolean, a character string, and then a list, another list within the list, and that list itself has heterogeneous things within it. So there's nothing wrong with that. I can type it, I can print out the name, it'll print out what that thing is. I can index into it. Remember again, Python is 0 indexed, and I can doubly index in to get into the nestedness. So if I do that, arg, what the hell's going on? Okay, so you see I've pulled out the third element, which is actually the fourth element, and I've pulled out the 0th element of that, which is the 5 within the 5, 7 blue. Interestingly, if I make a copy in Python, let's see. So I rewrote, I changed what the second element of my original data list was to be a new list instead of having same, which was the original second element or third element. And I can do object-oriented stuff where I tack on a list to another list. So for example, I can extend orig data, which was my copy of my original list, with the new version of data. And now if I look at orig data, we can see it's got all of this stuff packaged up in it. And I can actually sort this, and presumably there's some underlying rules in Python for how you sort disparate sorts of items. But you can see it's come up with some sorting that sort of makes sense, at least that well, maybe, I don't know. It's not in the same order it was before, at least. Okay, so let's stop there, and we will pick up and probably finish off the Python unit on Friday.